Hey guys, welcome back to the channel. I have another instrument cluster repair video. This is actually a test after the repairs. I was resolder, changing a few diodes and some of the circuitry for the fuel levels sensors, and also due to a high ampere draw on the instrument cluster, which I want to show now that it's all working properly. So I have mapped out the entire board to get to the signals all the way down to the microprocessor. I have one mark in here. Hopefully you can see that little black mark in there. That's one of the fuel level sensors in the instrument cluster. As usual, well, this is the way the face looks. This is an incandescent uh, cluster, so this is actually a very special phase and uses that transformer because it uses a lot of voltage, let's say. All right, so things that I want to do because I want to do the test without needles and the whole phase, and then I'm going to put it together and retest to make sure everything is still working in a good working order. As normal, and you know I do my homework on everything, so this is pretty basic, pretty hard to do any test as far as no communication with the scanner. This vehicle uses, let me see if I have, let me see. Well, these are the main powers and grounds on the instrument cluster. We have connector C1, C3. Those are the ones that control everything. I have marked it on here since I don't have the car, C1, C2, and C3. This is an empty. So you can see what we need in there. On C1, we have COM-B bus, and that is it's an internal bus for head module and other things that communicate. The instrument cluster will receive signals from CAM C, which is the powertrain control or bus. Let me see if I have the CAN B. Yeah, this is CAN B. As we can see, the instrument cluster right here will connect to the module, the total integrated module, to get communication from CAN C, which is at the end where the powertrain and all the stuff, because temperature or pressure, that will come as a message. The only thing that is directly connected to the cluster are the fuel levels. So I have in here mapped out the fuel level sensor. Those are in connector C2. We have the ground for the sensors, and then fuel level 1 and fuel level 2. This is like a horse saddle type fuel tank. Fuel level 1 is the main one, and fuel level 2 is on the, I think, passenger side. When it's more than half a tank, the computer will use both signals and one average to tell you how much fuel you got. When you have less than less than half a tank, we'll use only fuel level 1, and that is reading all the information. Let me see what I got here. This is a good information from Michael Brown that I found in Identifix. He said the fuel level, the sender resistance should be around 1,000 ohms when empty and about 50 ohms when full, which equates to 7 volts when empty and half a volt when full. The rest you can read in here. Let me see what else I have in here. I think I have the original diagram. Yeah, this is just a testing that I was getting in here for my test, obviously. It's the same thing. We have C2 ground and pin 16. This is the instrument cluster right above here. And then C2 pin 1 and 2 are the fuel level sensor signals. And then this is the fuel pump module connector, right? These are me, powers and grounds marked. These are the original diagram or pinouts for each connector. This is connector C1, which is a 26 pin. The cluster itself on the back right here, it will be a little hard to see, but they're marked in those which one is pin 1, pin 8, pin 3, pin 16, and all that for each connector. I always like, and I have to double check my connectors to make sure that everything that I am supplying is correctly. And yes, I double check everything and everything is good. I got connector C1, connector C2, which is where the field levels are. And we can see here B1 is field level signal 2, and B2 is field level signal or sensor signal, which is in number 1. And then connector 3, how it looks. I got the CAN bus explanation and voltages, which is very important because I was trying to see uh, the CAN bus on here. And it's a little different of what it's saying in here. And I'm going to show you that in a second because they're saying that CAN bus high should be 4.5 to 4.9, and actually it's actually the same because now that I remember reading this and we can see what it says in here, all measurements taken between the node ground and CAN terminal with a standard multimeter. So if I connect the multimeter in there, it will average. So this is not a 0 to 5 or something like that. There's just reading a voltmeter. And if I go over to picoscope, the mod, I mean the module, the instrument cluster is on. We'll see why those voltages are like that. So let me turn this on. It's just powering on. I gotta turn channel off. And we can see this. I'm going to sample capture. Let me do a zoom so we can see why it will be like that. So if we see CAN high, it's going from 0 to 5 volts, but it's very small signal. So that's why the multimeter will show 0.3 to 0.5 or whatever voltage is, right? In the other hand, CAN low is high to low. So it will stay in a higher voltage because we can see the pulse width is a lot higher compared to the low. In the high side is more low than high, and that's why the voltages are low in that one. So yes, that's what equate to what we are seeing in here, right? But yeah, short to power, short to ground, but this is for this communication. If we see the CAN bus B or CAN B, we can see they have AC heater, electric module, electric overhead, sunroof, door driver, passenger driver, because the instrument cluster is in control of what they call the lean bus. So we have mirrors, rain sensor, module steering control, radio amplifier, um, module passive entry and the radio, all connected to this CAN B. The integrated, totally integrated power module will be the gateway that will transfer data from this bus to the C bus, CAN C in case it's necessary, or to the diagnostic connector, which is completely isolated. If we see here, this is the data link connectors, pin 6 and 14 connects to the TIPM, totally integrated power module, right? And then the TIPM will have the connections. If I go over to CAN C, it will be there and we'll see everything. And actually, let me get that so we're seeing that too. Right, I downloaded the diagram from Identifix. And we see, because we see diagnostic, this should be CAN D, because if we go over to, let me see, CAN bus, yeah, CAN bus right here. At the beginning, we said that we have a controller network CAN D bus. You see, we have CAN C, we have CAN B bus, or on the higher speed CAN C or CAN D. The message structure, layout similar, which will control module, blah, blah, blah. So they're not really telling you that it's isolated. But if we see now here, CAN C, we have, anti-lock transmission, shifter, powertrain control module. All those are in CAN C, and that connects again to the TIPN, totally integrated power module. And then the data link connector is isolated and it connects to different pins on the TIPM, and the TIPN acts as a gateway. All right, so but that is for all the communications. I think I have expressed all the information that I want to share with this. Let me just show a few pictures that I did. I always take the time to mark the position from the needles. This is the front of the board with nothing and, all the needles and everything removed. I gotta go back the other way. So this is the other side. So these are the resting position of the needles. This has a stop, so I will just have to put them in there. But I know exactly the position. This is the connector for the actual phase of the instrument cluster. And I think that's it, right? Well, this is just me showing that I'm doing a test before. And this is, I just connected the instrument cluster as you can see before. And I was doing the information and doing some tests. And yes, I saw that we have a constant draw, which was also his concerns as well. For those that have anything to send over to me, let me just show you my website. So if you have a instrument cluster or a computer, that's the name of my website, My Salazar Diagnostics, and that is the first page you will land on. You can start a conversation with me if you click on this box right here, right? You just click on there. That will open your email browser or app, and then you can send me an email, or you can click on the Let's Chat right here on the right corner, and you can contact me. I always encourage people to please contact me first before you send anything like that. I can tell you if I can repair it or not. Not every module. I don't work in every single module and or every type of board. So please contact me first. All right. So going back into this test, what I wanted to show right now. Well, we have I have decade box in here supplying 180 ohms, and on the connector itself, which is the line that we're going to check, I'm seeing 3.2 volts. So going into the board, I have found I mapped the contact point for that signal, and it's right here. Oh, I need to turn this one on. I'm using this Fluke 289. I love this. This is a very, very powerful tool. I really like it a lot. All right, so let me now put that in there. We're in voltage. So I'm just going to touch in here. And we see that we got 1.98. So that is through resistors and some other things that are through the circuitry. And then the signal from here is just straight to the microprocessor. So I'm going to change this voltage. So we have, again, let me just read again. I think it's 1.9. That's what I said. Yeah, 1.98. All right, so I'm going to change the voltage. I'm going up. So this should now be higher than 1.98. And now we got 3.17. So the signal from the field levels sensors is reaching all the way to the microprocessor. So right now everything is in good working order as far as those two signals reaching the processor. So the next thing that we have, that he has, is parasitic draw. So right now we have 0.7. Obviously the cluster is still not asleep, and that will take a little longer. I can see no more activity on that buzz, but the actual cluster takes like, I would say maybe 60 seconds to go to sleep. And I want you to take a pic of that 0.69. That should go down to millivolts. And we will have some, and already did, 0.02. And we have, this is the draw. So we have in between this and this 20 milliamps of draw. So right now the cluster is going to sleep, which is correct. So this is now fully repaired. I'm going to stop the video, put everything back together. I'm going to have to completely reconnect because the way this is designed, actually I can leave this covered for last, and I can just put the phase, which is going to be the screen light, and retest. So let me just give me 1 second and I'll be right back. Okay, I got everything connected. This is pretty simple. It's, well, the way it is, let me change the camera angle. It uses 4 balls on the connector, so 2 on each side, and then that's the connector for the actual phase of the instrument cluster. All right, so let's put first ignition, and I mean battery, and you can see the uh, CAN bus coming on, and that is okay because it got first battery voltage. So that is completely normal. So let's power it up. All right, so this is completely powered up. We can see that everything is working good. And now let's power off. Let this go to sleep again for another, I don't know, maybe it was what, like 30 seconds or so? Let's keep an eye on that. Right now reading 690, 700 milliamps. All right, the can be buzz is already asleep, which is a good sign. We're just waiting for this to completely fall asleep and see that 0.02 20 milliamps draw, which is completely normal. That's the security lamp, which is again a normal behavior. Hopefully you see that red blinking in there. Try to record this live like that we see, make sure that nothing is, preventing the cluster to go asleep. I didn't have that connected, so that's why I would like to stress and do all the tests complete. The only thing that I now will now need to put is the covers and needles, but that I can do off camera to not make this already long video longer. It's taking a little longer to go to sleep. I can still not consider that abnormal. Can definitely see the buzz off. Let's see how long it's going to take. All right, guys, I paused the video just a little bit. It took around 2 minutes after I paused the video. So let's say, 3 minutes, but right now we have the 0.02. So definitely we have no more amp draw. So I'm going to put the cluster together and then contact this customer. I think it's Sugarland Shell in Leesburg, Virginia. They send this cluster to be repaired. So now your cluster is fully repaired. Just like I said, I need to reset the needles and then contact the customer to pick it up. But yep, no more amp draw. And all the circuitry from the or for the fuel level sensors is now intact all the way to the microprocessor. All right, guys, thank you so much for visiting the channel. Don't forget to subscribe. See you next time. Bye-bye.